Okay, so we're going to start off Fourier series and Fourier approximations by just going through some basics of what a sinusoid function is and how to fit curves with them. Alright, so far we've dealt with interpolation using standard or linear combination of standard polynomials. But now we're going to turn to another class that's really important for engineering, and that is trigonomic functions. So trigonomic functions of the form cos n of x or sine n of x. And why on earth would we want to work with these trigonomic functions? Well, in engineering we deal with many things that oscillate, believe it or not, even in civil engineering. Just think about when you are stationary on a bridge and a truck drives past. What do you feel? You should feel that the bridge moves. And that's something important that you're going to have to quantify if you wanted to, say, become a bridge engineer. And trigonomic functions can really help with this. And the reason why is because of the Fourier approximation. And we'll get into the Fourier approximation later on, but in short, it's really just a framework that describes how we need to use sine and cosine functions, because it deals with both the time and frequency domain. Okay, so now onto some mathematics. Well, we know that a periodic function, f of t, is defined as being equal to f of t equal to f of t plus capital T, where capital T is just the period of our oscillating function. So for example, you might have square waves or sinusoids, and we're going to focus on sinusoids. That is combinations of sine and cosine trigonomic functions. Now there's no clear-cut convention on which trigonomic function to use, but in general we can rewrite our periodic function terminology in terms of cosine. So I would write f of t is equal to a naught plus c1 cos of omega naught multiplied by t plus theta. So I'm just using the cosine trigonomic function, and at the end of this segment we will just discuss briefly if we had used sine. So now we have four values or four parameters that describe the sinusoid. So a naught describes the mean or the height above the abscissa. C1 is the amplitude height of the oscillation. That is, if we had some function that looks like this, C1 is the height of the oscillation. So it would be that term. A naught is the mean. In this instance, this is our x-axis. Our mean is at x equals 0. Omega naught is our angular frequency and tells us how often cycles occur. And theta is the phase, shift, or angle. And it tells us the shift horizontally in radians from t equals 0 at the origin here to the point of our new cycle. So here we would follow this wave until we get to this point in blue. So that would be our distance in radians from t equals 0 to the start of our new cycle. Okay, now the omega naught, which we said was our angular frequency, is defined as 2 pi multiplied by f. This gives us a unit of radians per time, or cycles per time, and the frequency f is equal to the inverse of our period. But now in its current form, f of t is quite difficult to work with because of our inclusion of the phase shift. But we can use the basic trigonomic identity to resolve this. So C1 cos of omega naught t plus theta can be rewritten as C1 multiplied by cos omega naught t multiplied by cos of theta minus sine of omega naught t sine theta. So now f of t can be rewritten as f of t being equal to a naught, which is the mean, plus a1 cos of omega naught t plus b1 sine of omega naught t, where a1 is equal to c1 cos theta and b1 is equal to negative c1 sine theta. If we wanted to calculate our phase shift, theta, we could just divide a1 and b1. So theta is equal to arctan negative b1 over c1, a1. And just to note that if a1 is less than 0, we would just add pi to theta. And we can calculate c1 because it's equal to the square root of a squared plus b squared. So this gives us these identities allow us to carry out our Fourier approximation, or even fit a sinusoid to a function value, and we're going to look at that just now using least squares approximation. And just a note on, if we had used sine instead of cosine, we would have had the following. So sine of omega naught t plus delta is equal to cos of omega naught t plus delta minus pi over 2. This is just telling us that cos is related to sine by a phase shift of 90 degrees, and in other words, our phase shift theta that we had identified earlier is equal to delta minus pi over 2. Alright, so let's just get into how we can use least squares to fit a sinusoid.